Okay, let's get started. This is a video on the constant of integration when we learn to integrate. This is another free video as part of my educational services. This is a math topic. My previous and first video was a physics topic on projectile motion. So today we're going to talk about the constant of integration. When we learn to integrate, we just get told to stick on this constant to an indefinite integral. And we often have some vague idea at that point of why we're doing that, or what it's for, or what role it plays. So we're going to look at that. We're going to look at it especially graphically, and we're going to look at what kind of conditions determine that constant. Why do we use it? What's it for? So let's start on the document scanner here. And we're going to start with a function that you should be familiar with if you're talking about calculus at all, x squared. That's just a parabola. And I'm going to take the derivative of that function, and I get 2x, which is a line. And I could go the other way. I can integrate 2x, and I get x squared. But I need to add the constant, which after a while you start to forget because you're not doing anything with it, or you're only infrequently doing anything with it, and you just start to forget about that. And you lose points on your quiz or test, and you get told to add that constant. Well, we need the constant because if I take the derivative with the constant, I still get the same thing, the 2x, because the derivative of a constant is 0, and it just goes away, right? So let's look on Desmos and have a look at what this means on the graph. Okay, so here we are on Desmos, and here's our line, y equals 2x, and here is our parabola, it's x squared plus c. And I have a variable c. It's set up as a slider. If I leave it off, I just get my parabola with the vertex at 0, the origin. So changing c moves this up and down. If you look at this equation, you can actually see that it's y minus c equals x squared. Y minus c is a translation in the y direction. If you move it up, it might start to look smaller. That's like a that's it because you're looking at the bottom part of it. You're looking at a smaller part of it. So we have to find what we have as a solution is basically a family of curves. All these curves satisfy the integral. Which one do we want? Well, that's what we determine with the c. So let's say we have a point like 4, 9. Okay, we know maybe we know that point from making a measurement in the lab, or maybe it was given to us in the problem, but in reality it could be a measured point or an observed point, and the model we come up with needs to go through that point. So we change c, and actually it goes through here at -7. So when c is -7, I go through the right point. Let's add the document scanner back in here a minute. And so my point is 4 and 9. That needs to be on my graph. And a lot of times you're not doing this on Desmos. You're doing it at home as homework or on a test. So you're going to do it graphically. I want to show it graphically, the significance of it. But we always solve this x squared plus c has to equal y, so 4 squared is 16, plus c is equal to 9, and c is -7. So we can find that, and usually we do it that way. But on the graph, we can actually see that changes. So let's go back to just the graph. If I have a different measured point, then I have to change my constant. So now if I want it to go through this point, minus 1 and 2, I need to set the constant equal to 1. And you can go back and solve that the way we just did the other one. Okay, the other question here is, does moving this around change, we use this for slope and area. Does that matter? So let's put it back at 0. The straight line is the derivative. The derivative gives us the slope. So the parabola has a 0 slope right here at the bottom, and the value of the derivative is 0. They happen to be equal here, but as you go up higher on the parabola, you get a steeper and steeper slope, so the value of the derivative goes up, and that's a linear function. That's not going to change when we change c. Okay, I still have a 0 slope down here. The slope gets larger as I go up, and that relationship doesn't really depend on c. So let's look at area. So let's say I want to go between 2 and 5. The integral should give me the area of the line under the curve. So when I integrate from 2 to 5, I should get this area right here, bounded by the straight line and the axis, 2 and 5. So let's evaluate that integral. Up here I have 17. And down here I have minus 4. So I get 21. Let's go back to include the document scanner here. So up here I had 17, and down here I had minus 4. 17 minus minus 4 is 21. That should be my area. Let's change C. Let's move it up here. We can move it up here, but we're going to have to zoom out a bit. Okay, up here I have 5 and 28. So I have a y value of 28. And at 2, I have a y value of 7. So I still get 21. Okay, this point includes my constant c of 3. And this point includes my constant c of 3. And when I subtract, it just goes out and it doesn't make any difference. And we can easily verify that area. The area of this triangle from the origin to 510 to here, the base is 5, the height is 10, so the area is 25. The area of the small one is 4, 1/2 times 2 times 4. So I have to subtract that. So I have 25 for the full triangle, and then 4 for the small one I take away, and I get 21. So this constant doesn't really matter in terms of that. And we're taking a definite integral in that case, and we're making a subtraction or difference, and so it just goes out. So let's go back to document scanner here and look at another problem. This time let's use 4 over x squared, and I want to integrate that, and so I'm going to get 4 times the integral of x to the minus 2. That's minus 4 over x plus my c that I don't want to forget that we're going to look at here. And we can check that. The dx of minus 4 over x plus c, this is equal to 4 over x squared. And the c has no derivative. So this is also going to have a constant. Let's, before we go to decimals, let's put the same point in here. Let's 4 and 9. So let's say that this is going to be my mathematical model or representation of something, and this point from an observation or measurement needs to be on there. So minus 4 over x, which is 4, plus c has to equal 9. And so c is equal to 10. Minus 1 plus 10 will be 9. So my full solution here will be minus 4 over x plus c, or plus 10. So let's look at that function now. Let's see. So go back here to Desmos. Let's clear off our previous functions and our limitations here. And here is our new function. And here's our point that we want to go through. So we can change the constant until we get through that point. And if the constant's 10, we now go through the point. We meet the necessary condition. Now we figured that out first on the other paper. We could choose a new point, like 2 and 5. Now I have to change my constant again. I have to lower it. Let's bring it down a bit. Or I could do minus 1, 2. Now I'm going to have to pay attention to the left side, in the second quadrant. So, and you can calculate those on your own, but c is minus 2, you'll go through that point. So we need to know some point in order to find this constant c, and it allows us to meet that condition. So where do these conditions come from? Let's go back here first. The original function is 4 over x squared. So this original, this 4 over x squared is the slope. So as this function gets out here, the slope is essentially 0, very close to 0. Here the slope gets very large, but it's positive, and here the slope gets very large and positive. So that's what the relationship between the derivative and integral look like. Okay, so let's look at why we have these conditions, and we'll finish with that. Let's go back to the document scanner, document camera, and look at a couple of simple examples of where we apply this constant. So my last video was on projectile motion, which used equations of motion, and we have velocity as a vector equation. Velocity equals my starting velocity plus acceleration times time. So acceleration is speeding up, and how long I speed up determines my speed, and I may have started with some speed. The distance is the integral of this. So I'm going to get vi times t. This is just some constant, so I'm going to multiply it by t. Here t is going to become 1/2 t squared, and I still have my acceleration. And I have a c from integrating. It's the integral of v. So what happens if t is equal to 0? And we often ignore this in physics because if t equals 0, we often call the distance or displacement 0. But it might not be. And so my actual full equation is the vit plus 1/2 a t squared plus my initial position. This is the c. And this function is going to change depending on where my starting location is. Another example would be when you're calculating something like a vibrating string, okay, something like a guitar string. So at one end I have a nut, at the other end I have a bridge, and these are two conditions. They're going to pin down my equations because the string can't move at the nut or the bridge. So the vibration is going to look like this. Or I can have harmonics like this. If I change my boundary condition, okay, so this other one, this physics one here, call this an initial condition. So and this is a common type of problem in physics and engineering. I have an initial condition related to where I begin. Okay, this one is a boundary condition. It's not related to when I start, it's related to some boundary in the problem. And if I change the boundary and I make the guitar longer, I'm going to have a different length of vibration. And I'm going to have different constants in the equations I solve. And I'll have a different harmonic in the middle. So our conditions determine that. And then that will determine, of course, how tight we need to tune the string. We can get it back in tune if we change the length by changing the tension. But that's more of a physics problem. So this is, so that's what the constant does. When we integrate, we're actually finding a family of curves and a set of solutions, an infinite set of solutions. In order to find the one we want in an engineering or science problem, we need to have a point, and then we have to find the curve out of that set that goes through that point. And this is still often not very clear when it's first introduced in calculus. It's just this mysterious C that we add on. Showing this family of curves, which is easy to do today with things like Desmos and computing, makes it easier to provide this insight. When I was studying at RPI, the first time I saw something like this, where I saw a family of curves, it was in differential equations, and it was on an overhead projector. So it was very hard to explain visually what this is or why we need this. Today, this is much easier. We have much better tools. And there's really no excuse for math courses not to give some insight here into why you have this constant. You don't just tack it on because it's required on the quiz. It's actually an important part of applying this math to a real-life problem. When you have some initial situation or you have some boundary situation. So that's enough about constants of integration, and we'll finish with that. I do offer tutoring. I'm working on perhaps teaching some courses in the near future. If you have questions or want to arrange some tutoring, I can help one time only. If you have some just short-term problem, I can set up ongoing meetings, regular tutoring. And I do offer some free help depending on my time and the problem and how interesting it is. But there's several Facebook groups where I have been helping problems. This one did not come from one of those questions, but it did come from an actual coursework problem. We were working on the constant of integration, and I realized that people don't really know what this is or why we're at it. Okay, so that's it for this video, and just get in touch with me if you need any math help. Bye.